Prove that if A is an element of the real numbers, and A is strictly greater than 1, then the set A squared, A cubed, and so on, is not bounded from above. Hint, first find a positive integer n such that A is strictly greater than 1 plus 1 over n, and prove that A to that n that we found, A to the nth power, is strictly greater than 1 plus 1 over n to the nth power, which is greater than or equal to 2. Now, there's a lot going on here, but I'm going to split this up into 4 different parts. So for the first part, we're going to go off the hint and prove that prove rather that there exists an n such that A is strictly greater than 1 plus 1 over n. And for the second part, I'm going to prove that A to the n is strictly greater than 1 plus 1 over n to the nth power. So the first part of this inequality here. And then for the third part, I'm going to prove that 1 plus 1 over n to the nth power is greater than or equal to 2 for any n greater than or equal to 1. And then for part 4, we're finally going to prove that the set A squared, A cubed, where A is strictly greater than 1, is not bounded from above. Bounded from above. Okay, and to give myself the maximum amount of room, I'm gonna clear the board here. So first, let's go to part 1 here. And before we're gonna prove that, let me just write it down here real quick. But before we prove it, we're gonna remember 3 particular facts that are gonna come in handy for proving this. So our three remembers are, number 1, and this is a fact that we use often, and that we will use often over the course of many proofs here on metaphor math. And so the first remember is, if A is strictly greater than B, and C is greater than or equal to D, then that implies that A plus C is strictly greater than B plus D. And I actually proved this in a separate video, and actually I prove all of the remembers that I will be talking about, and everything in red here, all the things that I preface with remember, I prove in a separate video, and I'll link them in this top right corner icon. If you click on that icon, you can find those videos where I prove these properties. I don't want to interrupt the flow of this current video, but I do prove these properties later. Don't take them for granted, but trust me for the purpose of this video. Trust me and take my word for it that they're true. So for property 2 here, given any epsilon greater than 0, so any real number, as small as we want, as large as we want, doesn't matter, there exists an n, a positive integer, n in the positive integers. This bolded z is the symbol for the integers, and the plus here denotes that it's the positive integers. So for any epsilon greater than 0, strictly greater than 0, there exists an n in the integers such that 1 over n is strictly less than epsilon. So what this is saying here is give me any epsilon as close to 0 as you want. I can always find an n such that 1 over n is closer to 0 than this epsilon that you gave me. So the third remember, and the last remember for this particular series of remembers, is that if A, or it's not if, actually it's going to be an if and only if statement, so A is strictly greater than B if and only if A minus B is in the positive real numbers. So now we're going to leverage all 3 of these things to prove that there exists an n such that A is strictly greater than 1 plus 1 over n, given that A is strictly greater than 1. So now we know for sure, like I said here, our given is A is strictly greater than 1. So using property 3 here, that implies that A minus 1 is in the positive real numbers. So that's nice. That means that A minus 1 is strictly greater than 0. So let's use property 2 here. Let's use property 2, and you might be able to see where I'm going with this. We can use property 2 here to state that there exists an n such that 1 over n is strictly less than a minus 1. So a minus 1 is in the positive real numbers. No matter how small it is, I'm able to find an n such that 1 over n is strictly less than a minus 1. So that's cool. So now we can finally use our first property here to say the following. So if a minus 1 is strictly greater than 1 over n, and 1 is equal to 1, which is obvious, but you'll see why I'm doing that in a second here, then this implies these together imply by number 1 here, by our first remember, that a minus 1 plus 1 is strictly greater than 1 over n plus 1, which is the same as saying that a is strictly greater than 1 over n plus 1. And we've done it. We've proven that there exists an n such that a is strictly greater than 1 plus 1 over n, given that a is strictly greater than 1. And the reason I was able to say here in the bottom here that 1 is equal to 1 is this property here. Well, of course we're able to say that 1 is equal to 1, but it works. We're able to use property 1 here, our first remember, because c could be greater than d or c could be equal to d. And no matter whether c is strictly greater than d or c is equal to d, a plus c will be strictly greater than b plus d as long as a is strictly greater than b. So we've proven 1. So 1, check. We've proven that there exists an n such that a is strictly greater than 1 plus 1 over n, given that a is strictly greater than 1. So that's nice. Let's clear the board to prove 2. To prove 2, we're going to have to, so let me write down what we want to prove first. So we want to prove, we want to prove that a to the n, that using that n that we found previously, a to the n is strictly greater than 1 plus 1 over n to the nth power. So now I'm going to ask us to remember another fact here that I'm going to actually prove in a separate video that I'm going to link up here in where this I is, and in the top right corner. So remember that if a is strictly greater than b, which is strictly greater than 0, so a and b are positive numbers, and c is greater than or equal to d, which is strictly greater than 0, so c and d are positive numbers, then, this is very similar to our addition one, where a plus b, that implies that a plus b is strictly greater than c plus d, but in this case, we're going to say that a times c is strictly greater than b times c. So if these two hold, then a times c is strictly greater than b times c. So let's use this to prove 2. So we can say that a is strictly greater than 1 plus 1 over n for that n that we found, because we know it exists, so we can just say it exists somewhere, so we technically found it. Or we didn't really technically find it, but we don't have to worry about finding a specific n. We know that it exists, so we can make the statement and we can say, okay, well, whatever that n is, we know that it exists somewhere, we'll just plug that in here. We don't have to worry about what it is specifically. So we know that this is true for that n that we know exists somewhere. So we know that this is true, and we also know, again, the same statement, a is strictly greater than 1 plus 1 over n, and I think you can see where I'm going with this. We can mark this as our a, this is our b, this is our c from our remember, referring back to our remember here, and this is our d. And so we can finally say a times a is strictly greater than 1 plus 1 over n times 1 plus 1 over n. And again, oh, by the way, that these numbers are greater than 0, because 1 is greater than 0, and 1 over n must be greater than 0 because n is a positive number. That's actually a separate remember that I'm going to prove in a separate video. If n is strictly greater than 0, then that implies that 1 over n is strictly greater than 0. So I'm going to prove that in a separate video, and again, I'm going to link it to the top right corner here. But so as to not to interrupt the flow of the video, we're going to just take my word for it that this is true. So we know for sure that these are strictly greater than 0, so we can use this remember here. And so this means that a squared is strictly greater than 1 plus 1 over n squared. rewriting what we had up top here. And then, so since this is true, and since also a is strictly greater than 1 plus 1 over n, and of course, again, these are all strictly greater than 0, so everything's strictly greater than 0, so we can use property 1 again. We have a squared times a is strictly greater than 1 plus 1 over n squared times 1 plus 1 over n. So now, and that's the same as saying that a cubed is strictly greater than 1 plus 1 over 9, oh, excuse me, 1 plus 1 over n cubed. And so repeating this process over and over and over, we can just iterate these steps, and we can finally arrive at any n. For any n, a to the n is strictly greater than 1 plus 1 over n to the nth power. For this particular n, actually, we can iterate all the way to this particular n that we know exists somewhere, but we don't know what it is specifically, but that doesn't matter. So we can iterate all the way to this a to the n is strictly greater than 1 plus 1 over n to the nth power. And this is true. Anyone can see, or I shouldn't say anyone can see, but it might be, given that we've done these previous steps, if you repeat these steps in your mind, kind of imagine us repeating these steps in our mind, then it's reasonable to see that a to the n is strictly greater than 1 plus 1 over n to the n. And if you don't see that that's okay, I encourage you to pause the video and rewind it, and kind of convince yourself that that's true, because it took me a while to convince myself of that as well. So now we've proven 2 here. We've proven 2. So that's good. We can now move on to 3, which is I wouldn't say harder, but it's maybe a little bit more technically challenging, where we have 1 plus 1 over n to the nth power. We want to prove that that's strictly greater than or equal to 2 for any n greater than or equal to 1. So for this, we're going to use this binomial theorem, and I'm going to encourage you to remember this again. Have another remember here. Remember that if I have a binomial raised to a certain power, a plus b raised to the n, or maybe I won't use m, let's use m, a plus b raised to the mth power, then that's the same as, it can be expanded into the sum from from k is equal to 0. Let me rewrite that here. From k is equal to 0 to n of a to the n minus k, b to the kth power, times the binomial coefficient n choose k. So now let's expand this out using this formula here. So we have, expanding that out, we have we have the sum of 1 to the n minus k times b, not b, our b in this case is 1 over n to the kth power times n choose k, from k equals 0 to n. And this is equal to, since 1 to the any power is just 1, and 1 times anything is just that thing, then that means that this is just equal to 1 over n to the kth power times n choose k. Now let's expand this out. Let's see what this looks like if we expand it out a little bit. So if we expand it out for k equals 0, so let's look at the case where k equals 0. So we have 1 over n to the 0th power times n choose 0, and I won't prove this here, it's worth thinking about why this is true. But the way to choose 0 items from a set of n items, there's only one way to choose 0 items from a set of n items. So that means that n choose 0 is just 1. So 1 over n raised to the 0th power, anything raised to the 0th power is just 1. So we have 1 times 1 here. And so this is for the case k equals 0. So I'll write a little k equals 0 here. For k equals 1, so we add to the case of k equals 1. So we have 1 over n to the 1st power. And then we have n choose 1. And if we have n items, so 1, 2, all the way up to n, if we have n items, let me get rid of this n here. If we have n items all the way up to n, then the way to choose one item from a set of n items, there's n different ways. I could choose the first one, I could choose the second one, I can choose the third, all the way up to the nth item. So there's n different ways to choose one items from a set of n items. Excuse me. Let me say that again. There's n different ways to choose one item from a set containing n items. So n choose 1, remember the binomial coefficient n choose k is, it means combinatorially that how many ways can I choose k items from a set of n containing n items. So this is going to be equal to, n choose 1 is actually n, so we have 1 over n times n, which is equal to 1 times 1 plus 1 over n times n is just 1. And then also, again, we have other terms over here, maybe, that are greater than or equal to 0. So it would be equal to 0 if n were to be equal to 1. So if n is equal to 1, then there would be no terms here. But if n is greater than 1, there would be extra terms over here, and these terms would be positive terms, because the binomial coefficient will be positive, and this will be positive. So we have terms over here. That are greater than or equal to 0. So I'll just say terms that sum, whose sum is greater than or equal to 0. So then this is equal to 2 plus a bunch of stuff I'll just say use our sum of terms whose sum is greater than or equal to 0. And so this must be, that implies that 2 plus u must be greater than or equal to 0. Because 2 is certainly equal to 0, and if this u, I won't prove it rigorously here, so I don't spend so much time, but you can do it for yourself. I encourage you to pause the video and do it for yourself and prove using property, the remember 1 from when we proved the first step in this video, way back when we proved the first step. Using property 1, you can prove that 2 plus u is strictly greater than 2 if u is strictly greater than 0. Now, I won't prove that here, but if u is equal to 0, then 2 plus u is equal to 2, which is equal to 2. So, no matter what, we have something that's 2 is either equal to, if in the case where u is equal to 0, or strictly greater than 2. So 2 plus u. So that implies, and this was, remember, this was the expansion, this was the sum of, way back when we did this was the sum, the summation expansion of 1 plus 1 over n to the nth power. So for any n strictly greater than or equal to 1, because remember I just talked about when n equals 1, these u terms will equal 0, and this still works, this inequality still works. So for any n strictly greater than or equal to 0, 1 plus 1 over n to the nth power is greater than or equal to 2. And so we've done it. We've proven property 3. We've proven property 3. 1 plus 1 over n to the nth power is strictly greater than or equal to 2. So that's great. That's really great. So let me clear the board to make room for our final step of this proof, where we're going to prove that this series, or this set here, a squared, a cubed, and so on, is not bounded. It's not bounded from above. Now, or I should say, given that, this is important, actually, this is really important, given that a is strictly greater than 1. Because given that a is strictly greater than 1, because, that's our hypothesis here. That's what they're asking us to prove, or they're asking us to prove this, given that a is strictly greater than 1. So now let's do that. I'm going to write down something that we know. We've proven both sides of this equality up here. Both sides of this equality, or inequality, rather. And that means that a to the n, for the n that we found, and that or rather that we know exists, and we don't really need to know specifically what it is, we know that a to the n, there exists an n, such that a to the n is greater than or equal to 2, or not greater than or equal to 2. We can actually say a stronger statement. Since a to the n is strictly greater than 1 plus 1 over n to the nth power, which is greater than or equal to 2, we know for sure that a to the n is strictly greater than 2. So a to the n is strictly greater than 2. So that's really helpful for us, because we can use the following fact, and I'm gonna prove this in a separate video so that I don't drag on this video too long. But there exists arbitrarily, I'm gonna just say remember, but if you don't remember, I guess remember or just know, just know and trust me for now. But again, I'm gonna prove this. Don't take my word for it too much, because I'm going to prove this in a separate video. There exists arbitrarily large powers of 2. Powers of 2. So now, because there exists arbitrarily large powers of 2, this is going to come in handy to us. And you could probably see why, but let's talk about it rigorously, since we're practicing our rigor and proof writing. That's what we're practicing here. So suppose that our set a squared, a cubed, and so on is bounded from above. Well, that implies that there exists, so this is by contradiction. So suppose, for contradiction, because we're going to arrive at a contradiction, because we're trying to prove that the set is not bounded from above. So suppose, and I should say given a is strictly greater than 1. So that this implies that there exists some u, or maybe I shouldn't use a u. Let's say let's pick v. Let's pick v, since we haven't used v yet. There exists a v that is strictly greater than or equal to a to the n for any n in the positive integers, because any element in this set is of the form a to the n for some n in the positive integers. We know that for sure. Continuing the pattern, we have a to the 4th, a to the 5th, and so on. So we can say for sure that any element in the set is of the form a to the n for some n in the positive integers. So there exists some v that is strictly greater than or equal to a to the n. So now, since there are arbitrarily large powers of 2, we can say for sure that there exists a power of 2. Let's just call that power of 2, I'm going to call it t for 2, t, which is strictly greater than v. There exists a power of 2 strictly greater than v, and I think you see where I might be going with this. So let's go back to our original statement, a to the n, well, not our original statement, but our statement that I introduced this train of thought with. A to the n is strictly greater than 2. Whoop. A to the n is strictly greater than 2. So let's use that. A to the n is strictly greater than 2. So what does that mean? We can use our remember that we did beforehand. Remember. So if a is strictly greater than b, which is strictly greater than 0, and c is greater than or equal to d, which is strictly greater than 0, then a times c is strictly greater than b times d. So we can use the same thing here. So a to the n is strictly greater than 2, and a to the n is strictly greater than 2. Label these a, b, c, and d. And I'll use them as quotes because we're replacing them with our remember that we have here to the right in red. So a to the n times a to the n is strictly greater than 2 times 2. Again, directly using this property here in red. And that's true. So a to the 2n is strictly greater than 2 to the second power. So that's nice. And of course you can see now, maybe you can see, and it's okay if you can't, but I'll go one more step. So we know that a to the 2n is strictly greater than 2 to the second power, and we also know that a to the n is strictly greater than 2, so that implies that a to the 2n times a to the n is strictly greater than 2 to the second power times 2, which implies that a to the 3n, rather, is strictly greater than 2 to the third, and so on. And so on, and we can iterate this process for as long as we want. So we know that this t that we found, t is equal to some 2 to the power of, I'll say, what letter haven't we used? 2 to the p, 2 to the p, for some p. And we know that we can find a to some power that's strictly greater than this 2 to the p, because we just proved that a to some power, and I'll say, again, we have to find a letter, r times n will be strictly greater than 2 to the r for any r. So no matter how big of a power of 2 we have, I'll always be able to find an a to the r times n, where n is the n that we found way back when, a to the r times n that is strictly greater than 2 to the r. So we know that there exists, or that we can find not only that we can find, but a to the p times n is going to be strictly greater than 2 to the p, which is equal to t. So a to the p times n is strictly greater than t. But look at this. A to the p times n, a to the p times n is an element of a squared, a cubed, and so on. And this t was an arbitrarily large power of 2. Well, it's a specific power of 2 that we said exists, that has to exist, we said is greater than v. But v was supposed to be an upper bound, for this set. And so we've arrived at our contradiction. That there can't, if we were to assume that there would be an upper bound, then we're able to find an element in this set that is strictly greater than that upper bound. And thus, it cannot be true that there exists an upper bound for this set. So thus, this set cannot have an upper bound.